Okay, we're on video 2 for the Unit 6, Day 1. This is labeled wrong here, but it is Unit 6, Day 1. So looking at what we talked about velocity being was the slope of that displacement time graph, we know that the derivative of a function measures the slope of the function at a certain point. Now in the piecewise linear graph, we really just had the slope of each component, but for nonlinear graphs, we're going to use the derivative of that displacement function that will be the velocity. So that's how we're going to find the velocity. So the velocity at any time t is given by the derivative of the displacement function. Now, the displacement function is typically shown with an S, and velocity would always be shown with a V. Now, we can also write that as ds dt, which is the derivative of the displacement in terms of time. So we know that the rate of change of the position is the velocity of that object. Okay? So we can continue looking at different velocity time graphs. So here we see that the velocity, and again, be really careful if you're asked to look at graphs at what your scale is measuring. So my y-axis there is measuring the actual velocity. This looks almost the same as the other one. I think it might even be the same, but now we're not looking at the displacement. It's just what would this be if it was velocity. So we start off with a velocity of 0, and the velocity is increasing. So the velocity goes from 0, I think this is meters per minute, up to 60 meters per minute over the first 10 minutes for our units here. So in this segment of the graph, so between 0 to 10 minutes, velocity is positive and increasing. Okay, so in this first segment, the velocity is positive the whole time, and it's going from small positive values to bigger positive values. And what we're going to look at that as when something is speeding up, we're going to talk also about acceleration, which is the rate of change of the velocity. In the next segment of the graph, this horizontal segment, when we looked at this as a position time graph, the horizontal segment meant staying still. Now, if this is a velocity time graph, this horizontal segment doesn't mean staying still. That means a constant velocity. So between 10 and 15 minutes, that's a constant velocity. Of 60 meters per minute. Okay, so again, the meaning of this is different based on what the actual graph is measuring. The next segment of the graph, we can say between 15 and 30 minutes. We would look at this. Here, the velocity is positive. So my values of velocity are still positive, but they're decreasing. So velocity is positive, but decreasing. What that actually means is that this will be slowing down. So here, where the velocity was positive, but then getting bigger and bigger positives, that would be speeding up in the first segment. Then it was going a constant velocity, and then the velocity is positive still, but it's slowing down. In the next segment, say between the 30 and the 40 minutes, now my velocity has moved into the negative. So now this velocity is in the negative segment and it's also still decreasing. So negative and decreasing actually means that that's going to be speeding up. So this will be going faster and faster because here it's going maybe -10 and then it's going -20, -30, -40. So not talking about actual value of the velocity, but looking at the magnitudes of those, that's speeding up. And we'll come to that a little bit later as well. The last segment, 40 to 60 minutes, here, this last segment in here, the velocity is still negative because it's below the 0 in where I'm measuring the velocity, but increasing. So it's negative, but increasing. So if negative values are increasing, so say going from -40 to -30 to -20 to -10, the speed of that, the magnitude of the velocity is actually getting smaller. So this is slowing down. And that's one of the hardest things, I think, for people to kind of visualize in this section. So I want to talk about this kind of as we go through different points on this graph. So again, I'm just going to kind of move my pencil back and forth, and I'll point at the piece of the graph. So for this part, the graph, the velocity is positive and increasing. So it starts off with a slow velocity, then it goes faster. Here, it's still staying at that same velocity. So the first segment would be moving slowly to the right, then faster to the right. The second segment, so this horizontal, would just be moving at a constant speed to the right. The third segment, so between the 15 and the 30 seconds, it's moving to the right, but it starts off fast and then it's slowing down. Okay. This point here, which I maybe should have highlighted a little bit more, at t equals 30, the velocity is 0, so that's stationary. Just for a second. So the first segment starts off slow, speeding up to the right. The second segment, consistent, same speed, constant speed. The third segment starts off fast because the velocity is big and it's slowing down, but still moving to the right. So it starts off fast and then it slows down. When it gets here, it's stopping. So it's doing this slow down, stops. When the velocity moves into the negative, now we're moving to the left. So this is moving in the other direction. Starting off little negatives, then speeding up really fast. So in through here, it's moving to the right, fast, slowing down, stopping for a second, not even a second, just an instant. And then it starts moving to the left, slower, and then faster, faster, faster. Okay. After 40 seconds, it's still moving to the left, but it was going really fast, and then it's just slowing down almost to a stop. So I hope that makes sense in terms of the real life application of what you would be seeing in any of these. So the velocity time graph tells us a few things. The first thing it tells us is the direction of movement. So if v is greater than 0, it's moving right. If v is less than 0, it's moving left. And obviously at those points where the velocity is equal to 0, that would be not moving at all or stationary. It also tells us whether it's speeding up or slowing down. So the slope of the velocity time graph, so how the velocity is changing, is going to impact whether it's speeding up or slowing down. I will say that it's not as straightforward as just whether it's increasing or decreasing. Because here, for instance, in this very first one, we said that that was speeding up. So where it was increasing, it was speeding up. And in this last segment from 40 to 50 or 40 to 60, we said that it was slowing down. So we're going to look at that when we combine velocity together with the next idea, which is acceleration. So we are going to talk about the rate of change of the velocity, which is acceleration. And that explains the slope of the velocity time graph. So if we were looking at this velocity graph here, we have another graph with velocity and time and no scale on this one. So we're just going to be a little bit more general. So in this one, we see that velocity is always positive. Okay. So we're always moving to the right. And that in the beginning, the velocity is increasing very quickly. So remember, the slope or the rate of change, that IRC, or the slope of the tangent, is really big here. So it's increasing very quickly at first. And then if we kind of look at the rate of change by drawing those tangents, it levels off. And at the end, it's not changing very much. Okay, so velocity is increasing fast at first. Then the rate of change slows down. It's still increasing, but just a tiny little bit towards the end there.